Hello everyone! You have really been loving my solid design principle videos, so here's the third one, which is going to be covering the Liskov principle, which in my opinion is one of the most important principles for writing really good object-oriented code. So let's get started with that right now. Welcome back to Web Dev Simplified. My name's Kyle, and my job is to simplify the web for you so you can start building your dream projects sooner. So if that sounds interesting, make sure you subscribe to the channel for more videos just like this one. And now to get started with the Liskov principle, I'm first going to read off the definition, which is that if S is a subtype of T, then objects of type T may be replaced with objects of type S. And that is a mouthful of jargon that really doesn't make too much sense, but essentially what this is saying is if you have an object, a class, let's say for example you have a class of animal, every single place that you use the animal class, you should be able to replace it with one of its subclasses. So if you have another class called dog, which inherits from animal, then every single place that you use animal, you should be able to use dog, and it's going to work just as well as it did before. That is what the Liskov principle says. Anywhere that you use one type of class, you need to be able to use all of the subclasses of that class, and it should work just fine. So let's jump into an example where we have two different classes. We have a rectangle class, and then we also have a square, which extends rectangle. And that is because we know that every single square is going to be a rectangle, because every square is a four-sided object, and a rectangle is also a four-sided object. So we know every square is a rectangle, but not every rectangle is a square. So that's why we have the relation in this direction, where a square extends rectangle. And all this is it takes a constructor, which gives you the width and height, and then there's a function for setting the width, setting the height, and then getting the area. And then inside of the square, we changed our set width and set height. We actually don't even need this area. We changed our set width and set height so that it's always going to set both of the sides, the width and the height, to always be exactly the same, so that it's actually a square and not a rectangle, hence why it's in the square class. And then we created two rectangles down here, we increased their width and then printed them out. And this increased width function, all it does is it sets the width of the rectangle to one more than what the width currently is. And as you can see, we have two rectangles. This one right here is 10 by 20, this one's 5 by 5. And so when we increase the width from 10 to 11, we get an area of 22, which we see printed on the right. And here, when we increase the width from 5 to 6, we get an area of 30, which is shown over here. But you may notice that this rectangle right here is actually a square. So we should just change this to be a square, change rectangle 2 to just be square, and we can come and replace all of our rectangle 2's with square, and we should see the exact same thing happen. Everything is going to be the same over here, right? 22 and 30, because we're now calling this increased rectangle width with a square, which is a subclass of rectangle. So according to Liskov's principle, all of this should work exactly the same as before. But when we run this, you'll notice we get 36 here as the area of our square. And that is because when our square enters this increase width function, it increases the width by 1, but that also increases the height by 1, because our width and height always are exactly the same. So now it is a 6 by 6 square instead of a 6 by 5 rectangle. So this function right here is breaking the Liskov substitution principle. Essentially, the problem is that our subclass of square is not actually compatible with every function that we're using a rectangle for. Our square cannot be substituted in place of a rectangle, so we now are failing that Liskov substitution principle. And this is sometimes a tricky problem to fix. But in this example, one of the easiest ways to fix this would be to change what we're inheriting from. So we want to create another class. This class would be, for example, shape. And this shape class here would actually just have this area function, for example. So we could have an area function, and it'll be implemented, and it'll do some kind of code in here to return the area. And then our rectangle is going to extend shape, and our square is going to extend shape. So now our rectangle and our square are both extending from shape instead of extending from rectangle. And now our API is going to work just fine, because when we set the width, for example, in our rectangle, it's going to modify just rectangle stuff. And we would need to have, for example, increase shape width. But obviously our shape doesn't really have a width, so this doesn't really work as is. But you get the point that what we need to do is we need to create an object that we can actually inherit the rest of our objects from. This example is more so just to show you how the Liskov principle works and how code that may look fine, this rectangle and square code we had before, is actually incorrect because it's violating that Liskov substitution principle. I have another example that I'm going to jump to where we can show exactly another way that the Liskov substitution principle is violated and how we can actually fix it. So here I have another example of the Liskov substitution principle, and we have 3 different classes. Our first class is our base class, which is a bird. And all of our birds can fly because birds can fly, so we have a fly function on our bird. Our next class is a duck class, which extends bird because it is a bird, and it has a quack function because ducks quack. And then lastly, we have a penguin function, or a penguin class, which extends bird because a penguin is a bird, and penguins can't fly. So we're throwing an error saying, hey, we can't fly, we can't actually do this. But we also have a swim function because penguins can swim, so it says I can swim. And then inside of here, we have a make bird fly function, which just calls fly on a bird. And then we're creating 2 different birds, duck and penguin, and then we're making them fly. And as you can see, the duck prints out I can fly just fine, but the penguin is throwing an error saying it cannot fly. And this is again another instance of the Liskov substitution principle not working. Because this is a bird function, so it expects a bird class. And we're passing in both of the subclasses of bird, duck and penguin. And according to the principle, every subclass of a class must be able to make this function work properly. And the duck function works fine. So this duck is passing the Liskov substitution principle. But the penguin class is not, because the penguin class cannot fly, and thus it works differently than its parent class, which can fly. So we're failing the Liskov substitution principle. And an easy way to fix this is to change it so that we don't just have a bird subclass, we have a flying bird subclass. So we're going to say we're going to have flying birds, and our duck is going to extend from flying bird, and then we're also going to create a swimming bird. And then we're going to put our swim method inside of there. So let's just copy that, paste that into our swimming bird, and of course, since our penguin can swim, it is going to be a swimming bird, and we don't need to worry about this fly function anymore. Now what we can do is we can make a flying bird fly, and we can have another function which is going to make a swimming, make swimming bird swim, and then we're just going to call swim here. So now we can say make flying bird fly on our duck, and we can make a swimming bird swim on our penguin, and you can see that works. I can fly and I can swim. And this code right here is passing the Liskov substitution principle, because every subclass of swimming bird is able to properly call this function, and every subclass of flying bird, in our case duck, is able to properly call the make flying bird fly function, and everything is working as if it was the parent class. The code doesn't know that you have a subclass, and because of that, it needs to work as if it was the parent class. But this code has a problem. And this is a problem I don't really want to get to in too much depth in this video, but it is a major problem with object-oriented programming and inheritance in general. And that's that a duck can also swim. So a duck can fly and a duck can swim, but we can't inherit from 2 different classes. You can't inherit from flying bird and from swimming bird. You can only inherit from one of them. So what we need to do is maybe create a 3rd class, which is flying swimming bird or something like that. And that really doesn't work very well as you get lots and lots of different permutations of flying, swimming, and other types of birds. So what a lot of times you're going to hear about is composition, which is the idea of adding in functionality instead of inheriting functionality. So we would add the swimming functionality to our duck and add the flying functionality to our duck without ever extending any base classes. And if composition is something that you want to hear more about, make sure to let me know down in the comments below, and I'll make an entire video of composition versus inheritance and why composition is so much better than inheritance. But for the purposes of this video, it's just important to know that as you start following the Liskov substitution principle, you may run into issues like this where you have really complex inheritance trees. And if you run into that problem, you need to look at composition as a way to solve that, because inheritance, when you get into situations like this, can become incredibly messy and is not the best way to write your code. But for most instances, inheritance is going to work just fine, and it's not going to be as complex as this, for example. All you need to know, though, for the Liskov substitution principle is that if you have a function that accepts a class every single subclass of that class must also be able to enter that function and work properly. That's all there is to the Liskov substitution principle. So while the definition is really confusing, it's an actually very simple principle to follow. And that's all there is to the Liskov substitution principle. If you enjoyed this video, make sure to check out my other videos linked over here and subscribe to my channel for more videos just like this one. Thank you very much for watching and have a good day.